All right, we're in 5.1. We're going to finish this one up today. We had left off on number 7, and we had found the tangent line. So we had our equation 3x squared minus the natural log of x, and we had found a tangent line at the point 1, 3 to be y equals 5x minus 2. So what I'd like for you to do is I'd like for you to graph both the original equation, this one, and the tangent line that we found last time. So on part B, we're asked to use a calculator to graph these. So that's what we're doing. Typically, I start out with a zoom 6 type of a screen, and then if I need to zoom in or zoom out from there, I go with that. The 6, as you remember, is the negative 10 to 10 on x and on y. And it's a little bit lopsided. It really looks like I don't need the left-hand side of the graph, which should make sense because we talked about the fact that the log graph itself does not have domain values that are negative. So we don't really need the left-hand side of the graph. And it kind of looks like on my graph too that I don't need the bottom part of the graph. So I'm going to eliminate both of those pieces by just making my window go from 0 on x minimum and 0 on y minimum. And I think that'll give me a little bit better picture, and it does. So it looks a little bit like maybe like a partial parabola, which should seem reasonable because part of the equation is 3x squared, which is parabolic. And then so it looks something like that. I'll draw it a little bit smoother. So that's the graph-ish, depending on your scale for the original equation. And then at 1, 3, we're about, say, like right here. That's just an arbitrary approximation because I don't have a grid marking here. And my tangent line seems to be crossing through there. Hang on. Like so-ish. So graphs are a good way to at least confirm that what your answer is that you've given or that you've gotten is reasonable, right? Because if this graph looked like, say, this, we would know there's something wrong. I need to go back and fix something. So while this graph doesn't prove that it works, it at least justifies that it's a reasonable answer. Yes, sir?
You said yesterday or whatever that ln is log x of x?
It's like typing your calculator. There's just an ln button, just natural log x. Like there's a button that says ln.
Okay, I'll find
right
it.
there.
Sweet.
It's just right under log, yeah.
Thank you.
It is log base e. The log in your calculator, which I didn't mention, is the common log, which is log base 10. So if you haven't done a lot with logarithms or haven't in a while, that's just a reminder. So log base 10 is the log that shows up in there. So our log we're doing is actually going to say ln. Okay, does everybody's graph look approximately like this? Okay, so I want to remind you one more feature of your calculator, and it's the derive feature, or in our calculator, it's approximated or abbreviated as inderiv. Do y'all remember that one? Okay, so you've got y1, you've got to put it into y1. Go into your regular screen of your calculator, and you'll hit math 8. And if you hit math 8, either it'll come up and it'll say inderiv, or somebody's going to have another operating system. Let me take a look at yours. It actually says d over dx, and it'll have a parenthesis here, and then it says x equals, and there's a blank spot right here. Okay, so one of these versions is what yours says. Mine says the first one. Probably most of yours say the second. Okay, does yours look like one of those two things when you press math 8? Excellent. The first thing that you tell it is you tell it what equation you have. Now, if you didn't have it already entered in y1, you could type it all in. We already have ours entered in y1, so the easiest thing to do is to tell it y1. And the way you get the y1, if you'll remember, is you hit vars. There's a button that says vars. It's over by the arrow pad. You go over to y vars because it's a y variable. That's what vars is. We're working with functions, so we select number 1, and we select enter on y1, and it should pull up y1 in the spot that you've got. Okay. The next thing you have to tell it is that your variable is x. Okay, so, and I bet that, Sophie, I bet you already did that, didn't you? Right here, you did, yeah. So there's probably a spot right here. Let me actually delete it out. This piece right here generally starts out blank, did it? Okay, so you have to tell it x is your variable. So the first thing you do is you put the x here, if it's that version, or if you've got the first version, you put comma x. Okay, And then you have to tell it at what x value you're looking. And so going back to our problem, what was our x value? Was it 3? Okay, so our x value is 3, so we put comma 3, or down here we would put a 3 here. Was it 3? 1. Okay, was y 3? I couldn't remember which one to switch. That's a problem. All right, 1, x is 1. Close your parenthesis. If you don't, it doesn't hurt it actually, but, and if you're at the other one, there's no parenthesis to close. Press enter. And what value does it give you? Ooh, it says 4.9 repeating. What is that really? It's 5. And that's a good place for us to remember that our calculator does not do calculus. Remember? Our calculator uses numerical approximation for the things that we do with calculus techniques. 4.9 repeating really is 5, but it's your best guess for your calculator as to what you're getting. So the 5 is the slope value that we got when we actually did it with calculus techniques back here. So that confirms the 5 part. It doesn't confirm the -2, right? But at least confirms the derivative value. Okay, does everybody remember all that? I know we've done that last semester, but just, it's been a month or two, right? Yeah, it's been a month or two. All right, let's take a look at the next one. The next one is bound to be the most favorite thing you did in Calc 1. No? Oh, okay. So I think it probably is. You just don't know it yet. Okay. And there's a reason we're encountering it again. You'll see why in just a second. But this one, I'm first just reminding you the way implicit differentiation works. That said, a few of you have learned another technique for doing implicit differentiation, and that's fine if you can do it successfully, but most of you who were trying to do it were not successful last semester. Just saying. So I'm going to continue to go down the road that I went down before and show it to you the way that I showed it to you before. Okay, so what we do when we do implicit differentiation is that we don't need it solved as y equals. Sometimes it's impossible to solve it as y equals, hence the need for implicit differentiation, okay? So we work through it with all of our normal derivative rules that we've seen before, and we remember that y itself is a function. So when we take the derivative of something with y in it, we use our normal rules, but then we're going to have a dy dx. That's the only difference when we take something's derivative that's got a y in it. So in particular, it starts with natural log of xy. Now remember, that means the x and the y are together on the inside of the natural log. So this is going to have a chain rule because we've got something inside of a natural log. It's also going to have a product rule because the x and the y are multiplied. Okay? So for starters, we're going to start with the natural log on the outside. This is our new rule that we started last time. What's the derivative of the natural log of something? It's 1 over it. So we're going to start out with 1 over, and that something here is xy. Then we multiply by the derivative of the inside. That's the x times the y. That's a product rule. The product rule says we rewrite the first piece, x. We take the derivative of the second piece, y. So what's the derivative of y? Dy dx. And then we do addition, and we reverse that process. Now we want the derivative of x. What's the derivative of x? That one's just 1. And we rewrite the second piece, y. Okay? Yes?
Okay, so you know how we have the rules? Would we be able to, do natural log of x plus the natural log of y?
You could.
Okay.
If you wanted to separate this as the natural log of x plus the natural log of y and then use those properties, you definitely could. And if you did it that way, you'll get the same answer. It'll look a little bit different sometimes, but it would look like this. And you'd have the 1 over x, that one's cool, but then you'd have the 1 over y, but you'd still have dy dx. But you would avoid the product rule. You're right. So both those options are perfectly fine. Okay? What's the derivative of the 5x? 5. And then the derivative of 30? 0. So let me actually, since you mentioned it, Sophia, we'll do it both directions so that we can see it all play out. Plus 5x equals 30 plus 5 equals 0. Okay. Okay. If you've done it the first way that I did it, you need to distribute that 1 over xy through the parentheses. Okay? So this is definitely the part that was tripping people up back in chapter 2 when we did it before, was what to do next at this point. A lot of you could get to this point or really close to this point. And then things would get kind of messy and you weren't sure what to do. So on this one, then we'd have an x over xy dy dx plus, and then it would have a y over dy plus my 5. I'll go to the other one that you mentioned second. Well, let's just finish this one out. Some of these things cancel, simplify, right? The x over the x, the y, oh, that shouldn't say dy, it should have just said xy, I'm sorry. It should have said y over xy. So the y and the y cancel here. And I'm left with 1 over y dy dx plus 1 over x plus 5 equals 0. And I think that's actually at this point where I already am over here. Do those match at this point? So good eye, like it would have been simpler for us to use our properties of logs on it and to do it this way. If there was addition and subtraction, we couldn't on the inside, but this one was multiplication. So at this point, we're at the same spot here as we are here. So let's actually solve it for dy dx. So first we need to move everything that's not multiplied by the dy dx on the other side. Yes?
Quick question. We have log y. Why is it running dy dx again? I'm sorry.
Say that again.
On the right side, we have log
Oh, okay.
y.
Yeah. So that's this over here. Let me mark it. This over here is a chain rule. Because y is a function, right? If we normally were able to solve for y equals, we would have to take the derivative of what y equals. But the derivative of what y equals is dy dx. We just don't have a closed form in which to write it. So we write it arbitrarily as dy dx. So we're going to move some of these pieces. This is 1 over y dy dx equals negative 1 over x and negative 5, right? And then what would I do to solve for dy dx? Yep, we'd multiply by y. So my dy dx then, in both versions of this, and I'll distribute the y through just so that we can see it. It's negative y over x minus 5y. You could merge these together, get a common denominator. I don't know if that makes it any better. So if you didn't, it would be okay, but that would be another version that you could see this written in. Okay, so why are we revisiting this other than the fact that it's just another piece that we could be using? The reason is because of what's happening next. That looks terrible. Agreed? This looks bad, right? Okay. Now, the directions don't just tell you to take the derivative. They give you a specific kind of way in which to do it. And the reason they're doing that is because it's a much easier way to do it, but you haven't learned it yet. So what we're about to do is called logarithmic differentiation. And it's going to involve implicit differentiation and logs. That's what it's going to involve. That's why we just did the implicit differentiation problem, not just because it was fun remembering back to Calc 1, although it was. Okay? So logarithmic differentiation is going to do exactly what Sophia noticed about that one, is it's going to use properties of logs. But if you look at this right now, you're probably saying, but Dr. Hans, there's no logs. And you're right. We're going to put them there. Here's the way it works. We're allowed, with algebra techniques, to operate just about anything we'd like to, as long as we do it to both sides of an equation. Agreed? We can multiply by 5 on both sides. We can subtract 7 on both sides. We can divide by things. We can take square roots, all that kind of stuff. And we can also insert logs. So it looks like this. We're going to take the natural log of both sides. The part at the end where it says that the x value is greater than 2/3, the reason that's there is because we will actually need to make sure that we're within the domain because we're about to put in logs. So it's there for the purposes of being mathematically accurate, but we don't have to do anything with it. Okay, so it's just there kind of space holding and making things correct for the next things that are following. Why in the world would that be helpful on the right-hand side? We can split it up, right? And we can split it up in a lot lot maybe more effective way than even the last problem was, although it was very effective to do so. This is even more so because I've got 3 pieces, I've got exponents, and I've got square roots. It's a mess. Okay, so remember, log properties say that if it's multiplication, like in the numerator, I can separate with addition. If I have denominators, that's separated with subtraction, and I'm going to do just that for one step. If you can do it all in one step, that's great. I'm going to split mine into 2 steps and use just that property first. So I'm going to have the natural log of x squared plus the natural log of the square root of 3x minus 2 and minus the natural log of x plus 1 squared. Is that good for everybody? We talked about those properties last time. Each one of these has a power. This is x squared. The one in the middle has a 1/2 power because of the square root. The one at the end has a power of 2 as well. All of those are the properties of repeated logs, which means you can pull the exponent into the front of the problem. So we can rewrite each of those, thus eliminating a portion of the chain rules that are going on, by the way. So 2 natural log of x plus 1/2 the natural log. It's still 3x minus 2. That's still a chain inside. We can't avoid that. And then minus 2 natural log of x plus 1. And all of this is equal to the natural log of y. So we haven't entirely avoided all of our more complicated derivatives, but we've avoided a lot of them, right? We've avoided the quotient rule. We've avoided the embedded chain rule, product rule kind of combination of things, yeah? And we're going to take the derivative of each of those pieces now sort of individually. Now we saw the natural log of y1 on the previous problem. What's the derivative of the natural log of y? 1 over y times dy dx. And in fact, this one's kind of friendly because that's the only y in the problem. Agreed? So everything else on the right-hand side is stuff we did last time. So what is the derivative of 2 natural log of x? 2 over x, or you could write 2 times the natural, or times 1 over x. How about the derivative of the 1/2 natural log 3x minus 2? I'm going to do it in pieces. 1/2 starts. What's next? 1 over 3x minus 2 times 3. We've got a derivative of an inside. There is a small chain rule there, a little bit of one. And then over here at the end, I have minus 2 times 1 over x plus 1. Okay? So that step right there is the only calculus step in the problem. It feels like this is a big calculus problem, but it's really a big algebra problem and some trig stuff, or some natural log stuff. Yes, ma'am?
Would this be something on a gateway?
It would not. We don't do implicit differentiation on gateways.
Okay.
No, there won't be any implicit differentiation or logarithmic differentiation on gateways. Good question. Simple rules, which doesn't mean that we don't include chain rules and product rules, of course, but nothing with implicit. Yep. Okay, everybody good so far? All right, so if, there's one more step for sure that's required no matter what, and even WebAssign would require it. We need to solve for dy dx. So I'm going to actually use another screen, and we're going to move this so I have more space. Okay, so we do need to multiply the other side by the y. I mean, like that's a necessary component. So we have dy dx. Whoops. X, there we go. And it's going to have each of these multiplied by y. And I'm going to write them all with the, I'm going to kind of condense some of these. So this is like 3 over 2 times 3x minus 2. Minus 2 over x plus 1. I'm not going to combine them any more than that at the moment. And then it's times y. Okay, so everybody good so far? All right. The problem is that the original problem had a closed form solving of what y is. Right? What is y?
Oh my gosh.
All of the stuff that's on the right. Yes? So we are going to replace y with what y is equal to. So over here, it's going to clean up far better than you might imagine at the moment. But this is an exercise in algebra without question. My y is x squared times the square root of 3x minus 2 over x plus 1 squared. All right. Our best hope for some of this to cancel, and some of it will, is to get a common denominator in what's going on the inside of that bracket, right? The part that we took the derivatives of with all the different logs. So that's what we're going to do. So my kids are in Algebra 1 right now, and they're working with far simpler problems than this, obviously. But we've been doing a lot of this lately, okay? So I know you can handle it, because this is way back to like 8th to 9th grade, and you've done it a lot, but just maybe not recently, okay? So I'm going to change colors to help us out, and I'm going to give us some more space by shifting some things around. All right, so the first piece needs to be multiplied by the denominator of the other pieces. So that's going to include the 2, the 3x minus 2, and I'm running out of space even more. Let's give it more space. And I need an x plus 1, right? So I got to do that numerator and denominator. The middle piece is going to need the x and the x plus 1. So not nearly as much. And the last piece, is going to need the x and the 2 and the 3x minus 2. Okay, conceptually speaking, does everybody remember all that now? Got to get the denominators all matched, and multiply by the numerators. Now we're going to do some algebra crunching, right? Some things that are simplifications with some algebra. There's no purpose in multiplying the denominator out. That's good news, because it means that I have less to do. I am going to put the 2 in front of the x, so I'm going to write it as 2x, and then 3x minus 2 and x plus 1. So all that's fine. And we're going to try and multiply out what's in each of the numerators and then combine like terms. So these two are going to give me, change the color again, a 4. So I'm going to have a 4 here, and then I'm going to distribute through the other two pieces together, and then I'll distribute the 4 later. So I have 3x squared. The outside 3x and the inside 2x are going to give me x. And then the ending is going to give me a negative 2. So if you watch me make a mistake, you're going to tell me something, right? Yes. Okay, good. All right. The next piece, we can actually distribute all of it really nicely because it's just 3x times the x plus 1. It's addition, so that's really nice. So I have 3x squared plus 3x. Excellent. And the last piece I can distribute really nicely all at the same time, probably too. This is all 4x. And I'll distribute it through with a negative, so negative 4x. So negative 4, times the 3, so negative 12x squared. And so negative 4, so it'd be positive 8x. That look okay? All this at the end, simply going to rewrite it for the moment. Okay, so we need to distribute the 4 through, and in an effort to sort of save a little bit of working space, I'm just going to write that through on top of it. I'll change colors again for us, and then we'll combine those pieces all at the same time. So this is now 12x squared plus 4x minus 8. All right, a lot of things are going to collapse pretty quickly. We have a 12x squared here at the beginning, and I've got a negative 12x squared at the end. That's nice. So that leaves me with only, I think, the 3x squared. Does that look right? Combining some pieces together, we have 4x, 3x, that's 7x. They're all positive, I think, and then I've got an 8x. So how many is that? 15. 15x. Okay, so far it's matching on my other paper that I've written it down on before, so that's good news. How about constants? I think it's just the -8. Is that right? That's my only constant. And it's over 2x times 3x minus 2 times x plus 1. It collapsed a lot. And then we have times our x squared and our square root of 3x minus 2, our x plus 1 squared. Okay, so some of these pieces are going to cancel from here and collapse really nicely. So I've got like the x squared here and I've got an x over here. So one of those is going to cancel. So that's going to leave me with one of these x's up here. The x plus 1s are going to combine. They're not going to cancel, but they are going to combine to give me 3 of them, right? X, they're going to have a cubed. This 3x minus 2 in the denominator and the square root of 3x minus 2 in the numerator also cancel. Does anybody remember how? It will. It'll give me a square root of 3x minus 2 on bottom. So you think about it in terms of exponents. I think that's the easiest thought. I'll explain one other option too. But this 3x minus 2 in the denominator has a power of 1. And this is a power of 1/2 in the numerator. So if you were thinking about like how do I subtract exponents, the 1 in the denominator minus the 1/2 from the numerator would give me a 1/2 in the denominator. You can also think about what happens when we try to rationalize things. Do you know when you try to rationalize a square root in the denominator, you multiply by it? And when you do that, it puts 1 in the numerator and it eliminates the radical part of the denominator. So this is kind of doing that in reverse. So these two pieces, this is going to cancel, and this is going to make this power 1/2. And then these two are going to combine with a power of 3. So let me shrink what's on this screen for the moment, because I think we're almost finished without moving to another screen. So we're going to distribute the x from the numerator of the second fraction through the first fraction. So this is 3x cubed plus 15x squared minus 8x. And then over here, there's still a 2 out front. That one did not disappear. I have a 3x minus 2 to the 1/2, or a square root of 3x minus 2. And then I have an x plus 1 cubed. It's not a good 3. That's better. And this would be dy dx. Any questions on that?